My name is Dante Sanvito, and today I will present our latest paper, syslrn, learning what to monitor for efficient anomaly detection. Monitoring software behavior to detect errors and issues is a critical task in any operational system deployment. A common approach is based on automated analysis of application logs. Logs are available in any software application, and they track the application state together with relevant events. Logs have a semi-structured format. For example, they include information related to the timestamp, the process ID, and a free text log statement. Typical log-based anomaly detection systems are based on 3 steps. Since log files can interleave entries related to different components and potentially concurrent execution flows, in a first step, we need to extract a group or sequences of correlated log entries. This step can be, for example, based on application-level identifiers. In the next step, log messages are converted into a numerical representation to make them suitable for automatic analysis. As shown in the figure, parsing, for example, abstracts away parameters from log messages to obtain the corresponding log templates. The last phase builds a model to detect deviations with respect to expected behavior, for example, in terms of execution flow. Examples of techniques here are based on invariant analysis or machine learning. We can make a couple of observations here, depending on the specific techniques selected at each step above. These systems require a variable amount of application-specific knowledge. This expertise is not reusable across applications and sometimes even across the software updates of the same application. For example, the format of log messages and the set of logged events can evolve over time. As a second observation, these approaches are intrinsically limited by when and what an application logs. Provenance graphs offer an alternative to log-based monitoring. A provenance graph is a graph capturing the relationships across operating system level entities, such as the processes, networks, and files, and is created by monitoring operating system events, for example, syscalls. The types and number of processes and also the relationships disclose relevant information about the application behavior and its state. These tools are, however, mostly used for security critical services and for offline analysis due to the increased monitoring overhead when tracking the entire state over time. Finally, moving from the security domain into the monitoring of failures, the detection of failures might require the monitoring of a smaller set of events. For example, the unexpected lack or presence of processes or relationships might represent a signal of failure. In this work, we propose an alternative to complement or potentially replace these approaches, which requires little domain knowledge, which is independent from software developer practice, and which is lightweight enough to be deployed in high-performance scenarios. From a high-level perspective, we split the problem into phases. In the offline phase, we perform detailed monitoring to identify key indicators of normal behavior. Then, in the online phase, we can execute a lightweight monitoring based on such learned indicators to verify the correct behavior of the system. We can now enter in more details about the 2 phases. In the offline phase, we build a complete system behavior graph by observing the system under normal operations and by collecting data. Here, the system can be temporarily instrumented or can be run in a controlled environment. In this graph, nodes represent processes and links represent their interaction. For example, process creation, inter-process, and network communication. We then run a set of graph analysis methods to identify relevant features, which are then used to derive a model for normal behavior. Since this phase is offline, we can afford to perform more sophisticated analysis techniques. In the online phase, we instead only collect relevant features which have been learned in the offline phase. Here, the monitoring is based on Linux eBPF, which enables to inject small programs at relevant kernel hooks and to efficiently collect the required information. During the online phase, the monitoring is driven by the application's external interfaces. The anomaly detection is periodically performed to detect a failure or an abnormal behavior. In this paper, we present a preliminary prototype of syslrn. We support a single graph analysis method, which consists of an heuristic based on a bag of components graph embedding and a set of linear regression algorithms. We tested our prototype with a use case based on OpenStack. While we plan to enrich our approach with several other techniques, these simple methods is already sufficient to provide compelling performance in this use case. In this work, we selected a use case based on OpenStack. OpenStack is a complex cloud management system that comprises several modules which interact among each other and also with third-party software to provide the requested services. We instrumented a testbed to perform common OpenStack operations related to the lifecycle of virtual machines. At the same time, we injected realistic failures in its component using a framework from the literature that we extended to support multiple workloads. We collected a series of application graphs from our OpenStack deployment. In the figure, we can observe an example of graph related to the provisioning of a single virtual machine. The graph includes system background processes, application background processes, and also processes related to the handling of the service requests. Let's now focus on this last class of processes. In the red square, we highlighted three types of processes which are part of this last class, and that shows the dynamic interaction between internal and external components. Specifically, the user request is initially handled by NanoCompute, which interacts with the libvirt that finally communicates with the QEMU KVM process to create the virtual machine. Interestingly, when the user requests to create 3 virtual machines, libvirt creates 6 QEMU KVM instances. Instead, if the virtual machine creation fails, only one instance of QEMU KVM is present. syslrn aims at understanding the behavior of the processes in relation to the received service requests. In the next slide, we will describe in greater details how this is achieved. So, in the offline phase, syslrn starts from the system graph and builds a vector representation called graph embedding based on a bag of components. For each node type, which in our case are the name of the process executable, the embedding defines 2 dimensions. The first counts the number of processes instances, and the second is the total count of their corresponding relationships. The next step is to learn the normal software behavior. We developed an heuristic to analyze the relationship between the features of the graph embeddings and the number of service requests received by the system. We fit a linear regression model for each feature and then select a subset of them based on a goodness of fit metric. In our data, out of 152 features, only 26 are selected. And interestingly, those features are related not only to OpenStack processes, but also to third-party software or operating system processes. As a final step, syslrn performs the features backtracking to map the selected features to the corresponding operating system primitives required to monitor them. This is what needs to be monitored at runtime by the eBPF programs. In the current implementation, the backtracking rules are defined by the system user, but in a future version, we aim at automating this step. In the online phase, instead, the collected features are periodically checked by the anomaly detection module against the model of normal behavior. The current implementation is based on an ensemble of linear regression models, and it verifies that all the features are linearly evolving according to number of service requests which are processed by the system. In our evaluation, we consider dplog as our baseline. Dplog is an anomaly detection system based on logs. Log entries are grouped into sequences using OpenStack instance ID as identifier. And after log parsing, dplog builds an anomaly detection system based on LSTM model, which is a type of recurrent neural network typically employed for sequential data. The default configuration of dplog considers a single identifier, specifically Nova instance ID. However, not all the failures injected in other components will be reflected in Nova logs. For this reason, we considered a second baseline in which we combine three dplog systems using three different log sequences, which are based on identifiers related to three different components. Specifically, we are using identifiers for Nova instances, neutron networks, and cylinder volumes. The combined system declares an experiment as anomalous whenever at least one of the three models detects an anomaly. We generated a dataset including more than 900 experiments. Each experiment is either failure-free or includes a single failure point in one of the stock components among Nova, Neutron, and Cinder. In each experiment, we run one or more homogeneous workloads, including all the operations required to create, start, stop, and delete a virtual machine. During the process, we collect both application logs and operating system level events. The first are used by dplog, while the latter are used by syslrn. Both systems have been trained considering only failure-free data. Indeed, both systems are unsupervised and builds model for normal behavior without assuming the availability of labeled anomalous data. Performance are evaluated using tenfold cross-validation. So the test set includes all the failures experiment and the failure-free data left out from the training fold. In terms of metrics, we considered recall and selectivity, which represents the true positive and true negative rate, respectively, and indicates the quota of normal or anomalous experiments correctly marked as normal or anomalous. We can observe that syslrn outperforms both dplog and this combined version, achieving around 2% of false negative and 1% of false positive. syslrn is able to naturally relate failures happening to different components and also to detect those failures that do not have any effects on the log, but that affects other processes in the system. One of the requirements of syslrn is the minimization of the monitoring overhead. We investigated the overhead of running OS level feature extraction with BPF using a micro benchmark. We selected Redis, which is a high-performance key value store that heavily relies on communication. We selected a different target application because the OpenStack virtual machine generation workload has a number of service requests over time, which is too low to perform a stress test. We generated a workload using a Redis benchmark tool, using 50 concurrent clients and disabling connection keep alive, so that we can ensure that connection operations are executed at each request. We measured the overhead, we measured the performance baseline in requests per second for different types of operations without performing any monitoring. Then we measured the overhead introduced by logging individual requests on the server side. And finally, we disabled logging and activated eBPF monitoring. As reported in the tables, logging can reduce performance up to 65%, an overhead which is over 10 times higher than eBPF. In most cases, logs are anyway required, but for some performance critical deployment, syslrn may provide a more efficient monitoring alternative. Conclusion: in this paper, we presented a first prototype of syslrn, implementing a minimal set of functionalities. Both the evaluation and deployment models are still preliminary. We evaluated a single use case with a simplified subset of workloads, and we made some simplifying assumptions. we could demonstrate the advantage of the approach compared to other state-of-the-art solutions. However, we plan to evaluate it on a larger set of applications to investigate benefits and limitations. We also plan to extend the syslrn with multiple methods for graph representation and normal behavior modeling. Finally, as a final comment, we release our dataset to enable the community to evaluate additional anomaly detection methods. The dataset includes the preprocessed graph data, but also the raw monitoring data from eBPF and Linux audit, and also all the OpenStack application logs. You can find the link also included in the paper. This is the end of my presentation. Thanks a lot for your attention.